Imagine the entire universe compressed into a single point. About 13.8 billion years ago, this point exploded. We call this moment the Big Bang. It was the beginning of space and time itself. The Big Bang set everything in motion, creating matter and energy. After the Big Bang, the universe began to expand, and it's still expanding today. Galaxies in our universe are moving away from each other. The Big Bang theory explains what we see in the night sky. It's our best understanding of how our cosmic story began.
The Big Bang Theory isn't just a wild guess, it's supported by strong evidence. One compelling piece is the cosmic microwave background radiation. It's like an echo of the Big Bang, a faint glow filling the universe. Discovered by accident in 1964 by radio astronomers Arno Penzias and Robert Wilson. This discovery won them the Nobel Prize in Physics.
Another key evidence is the redshift of galaxies. Distant galaxies' light appears redder due to the universe's expansion. These observations support the Big Bang theory.
The universe has a rich history spanning nearly 14 billion years. Let's take a journey through time, starting from the Big Bang. In the first fraction of a second, the universe was incredibly hot and dense. The universe expanded rapidly, doubling in size every tiny fraction of a second. After about 3 minutes, protons and neutrons formed hydrogen and helium nuclei. Around 380,000 years after the Big Bang, the universe cooled enough for the first atoms to form. Gravity caused matter to clump together, forming the first stars and galaxies. Our solar system formed about 4.6 billion years ago. We're made of star stuff, as Carl Sagan famously said.
The expansion of the universe is a fundamental concept in cosmology. It's not that galaxies are moving through space, space itself is stretching. This expansion affects everything in the universe, but it's only noticeable on very large scales. Gravity holds galaxies and solar systems together, so they don't expand internally. But the space between galaxies is growing. This expansion is accelerating, driven by a mysterious force we call dark energy. The rate of expansion is described by Hubble's law. Edwin Hubble discovered that the farther away a galaxy is, the faster it appears to be moving away from us. This relationship is key to understanding the universe's age and size. Cosmic inflation is another important concept. Inflation suggests that the very early universe underwent a period of extremely rapid expansion. This happened in just a tiny fraction of a second after the Big Bang. Inflation explains why the universe looks so uniform on large scales and why it is so flat.
While the Big Bang theory explains much about our universe, many mysteries remain. One of the biggest is dark matter. We can't see it or touch it, but we can detect its gravitational effects. Dark matter seems to make up about 85% of the matter in the universe, but we don't know what it's made of. Understanding dark matter is a major goal of modern physics. Another mystery is dark energy. This is the name we give to whatever is causing the universe's expansion to accelerate. Dark energy makes up about 68% of the universe's total energy and matter. But we don't know what it is. Is it a property of space itself? Is it a new kind of energy field? Or is our understanding of gravity incomplete? The Big Bang theory has given us a framework for understanding the universe, but it's clear that we still have much to learn. The cosmos continues to surprise and inspire us.
The Milky Way, home to billions of stars, rising and setting over billions of worlds, including our own. In this vast expanse, how did our sun, the Earth, and the planets come to be? In recent decades, our understanding of the solar system's evolution has greatly improved, but deep questions remain. To answer those questions, astronomers are preparing to visit someplace very small. Asteroid Bennu. A lump of rock and organic material, the early building blocks of the solar system, of Earth, of us. Bennu is a time capsule, and its journey takes us way, way back, 4.5 billion years. The raw ingredients of Bennu and our solar system originated in a stellar nursery, a vast cloud of hydrogen, helium, and dust. Our own sun doesn't yet exist, Nearby are hot stars like this one, quickly burning up its fuel and destroying itself in a colossal explosion called a supernova. The explosion destabilizes our cloud, causing it to collapse. In the geologic blink of an eye, 100,000 years, gravity and angular momentum flatten the cloud into a swirling disk. In the center, where molecules crash together tightest, a protostar revs up to incredible pressures and temperatures. Deep within the disk, clumps of dust not much larger than a grain of wheat are flash heated into droplets of molten rock, called chondrules. The source of this heat remains a mystery. Chondrules are destined to become the building blocks of the solar system. Coaxed by gravity and turbulence, the chondrules clump. They grow into the first asteroids, into mountains, into planets. The asteroids are rubble piles of rock, metal, ice, and organics. This large asteroid is the parent body of Bennu, a protoplanet whose size we can only guess. Closer to the protostar, a planet begins to form. And then, dawn in the solar system. The protostar undergoes fusion and ignites, revealing our sun. But the solar system is far from finished. Jupiter most likely forms near its outer edge, but just 500 million years after the sun ignites, some believe that it slowly moves inward. Its massive gravity ripples the asteroid belt, disrupting countless asteroids and comets, flinging them toward the sun. They rain down on the inner planets, hammering and remelting large portions of their crust. Did these impacts also deliver organics and water, key ingredients for life? Back in the asteroid belt, Bennu's parent body is lucky. It survives this period of heavy bombardment. The solar system cools and calms. Jupiter and its many moons assume the orbits that we see today. Billions of years of quiet follow, more or less. Then a billion years ago, one theory suggests a collision shatters the protoplanet. Some of the debris loosely coalesces into a new, smaller body, Bennu. But Bennu will not stay in place. Dull, non-reflective, it slowly migrates toward the sun. Solar heating turns its warm side into a low-intensity thruster. Through millions of years, Bennu's orbit gradually tightens until it interacts with Saturn's gravity, altering its trajectory and hurling it into the inner solar system. Close encounters with Earth and Venus follow. Their gravitational tugs may have repeatedly stretched and reformed Bennu, turning it inside out and pulling off loose material. As a result, it has no satellites of its own, until now. Today, NASA is sending a spacecraft called OSIRIS-REx to explore Bennu and retrieve a sample. Why? Bennu has survived its long journey and settled into a near-Earth orbit, bringing its secrets within our reach. Now it is ready to teach us more about the solar system's history, its formation, its evolution, and our own place among the stars.
India's Chandrayaan-3 moon mission has already proven historic. It put India in the history books for being the 4th nation to ever successfully land a spacecraft on the moon, and the very first to ever land at its south pole. The lander Vikram and the rover Pragyan already made discoveries that could profoundly impact our understanding of the moon's chemical composition and geological history, and has given the world vital data that will aid future return missions to our lunar neighbour. Chandrayaan-3 was launched on the 14th of July 2023. It was made up of a lander module called Vikram, a small rover called Pragyan, and an orbiter module that carried the other 2 components across the Gulf of Space. On the 23rd of August, Vikram, with the little Pragyan tucked inside, touched down on the moon's surface at the beginning of a lunar day. But time was not on their side. Chandrayaan-3 was a surprisingly cost-effective mission. While NASA's Artemis mission launches will each cost on average $4.1 billion, the entire Chandrayaan-3 mission only came to 6.15 billion rupees. With this lower budget came technological limitations. When the lunar night fell, Vikram and Pragyan would be subjected to temperatures of minus 120 degrees Celsius, temperatures they were not designed to survive. A lunar day lasts 14 Earth days. The Chandrayaan-3 mission would need to complete its major objectives in that time, as their odds of surviving to the day after that were slim. And so Vikram lowered its ramp, and Pragyan, the rover, powered up and headed out down onto the moon's surface. Pragyan is a 27 kilogram, 6-wheeled rover that came equipped with an alpha particle X-ray spectrometer for analyzing the chemical composition of the moon by firing radiation at it and seeing what wavelengths bounce back, and a laser-induced breakdown spectroscopy instrument that does a similar thing, but this time by firing a laser at the target of interest and analyzing the light wavelengths that are released by the resulting plasma. There's much we don't understand about the moon and its water cycles. There's growing evidence that the moon contains quite a lot of water, and yet extracting it will take understanding where that water can be found and how it moves throughout the long lunar days and nights. Is it affected by solar radiation? Is it trapped in hidden deposits? Although Chandrayaan-3 only lasted 2 weeks, which I'm sure is less time than ISRO scientists would have liked, it has offered us vital insights into the conditions on the moon. As far as water is concerned, at the very least, it has given future astronauts this one piece of advice. If you want to find a drink of water on the moon, you might want to start by bringing a shovel.